Thank you for thank you for great introduction. So can you hear my voice?
Perfectly.
Perfectly, yes.
Okay. So thank you for arranging this presentations. I'm going to introduce the research that I have done at Waterloo last 3 or 4 years. Okay, so the title is a human machine collaborated infrastructure assessment. Okay, here's the outline of today's seminar. I first introduce where is Waterloo, University of Waterloo, and then introduce my lab, and then I introduced this 3 different projects that I've done at Waterloo. Okay, so here's the Canada. All the largest cities are placed on the border between the Canada and the United States, and then Waterloo is in the Ontario. Okay, but the Ontario is really big, but all the big city in the near this border. So my university here is near the Kitchener. It's a 1-hour drive to the Toronto, 1-hour drive to the Niagara Falls. I think there is a very best location. So if you visit the Niagara Falls, you can stop by the Waterloo. Okay, so Waterloo is a science engineering oriented university. So one of the top engineering school in Canada. So, but compared to the other universities, the the key features in the Waterloo program. One is the trimester, second one is the co-op education. So unfortunately, undergrad students, there's no vacation. So there's the 3 term, winter, spring, and fall. And then so the students go to the industry every other term. So for instance, the fall term, they do take a course in the Waterloo in the fall term, and then winter term, they go to the industry and then do work. And then go back to the school and then take a course and then go outside again. So basically undergrad program is a 5-year program. So at the end of the undergrad year, they have a 2 years, the work experience. Yeah, that is really good for the students, get a much better job and then higher salary. But the issue is, there's no vacation. So, okay, there's a very tough program. Okay, so I joined the Waterloo in 2018. So my lab name is a Computer Vision for Smart Structure Laboratory. So I'm trying to develop some kind of the machine learning and the computer vision solution for the civil engineering applications. I have 3 PhD students, and then you can visit my website, and then you can see my current research project, and then you can see the YouTube video. I frequently upload my research video in the YouTube, so you can see those video. Okay. So among the many projects, I'm trying to, focus on some kind of the application for the visual inspections. We all know that visual inspection is challenging, is expensive, and then time consuming. Sometimes it is dangerous. I mean, all this photo is targeting for the bridge inspection, but this the visual inspection includes like a pipeline inspection or the plant inspections, where the inspection is actually go there and they're looking at the large space. Okay. So here's the example. So Ontario built this manual called the Ontario Structure Inspection Manual. So we call the OSIM manual. That involved the systematic inspections of all the highway structure in Ontario. Okay, so there's a detailed visual inspection standard. So this is the excerpt from the the OSIM evaluation for the burial. So all the inspector write down this information. So element and then all this background inspection. And also they need to do this condition evaluation. Okay, they evaluate the excellent, good, fair, poor, and then they measure those area. Okay, so basically in here, this is the general, the guideline how to evaluate those areas: excellent, good, fair, poor. So if you see this guideline, we first do the damage inspection. Okay, we detect the damage or the spalling or other types of the damage. Depending on this levels of the damage, we are, the categorize that this area is excellent, good, or fair. Okay, this is the guideline for the spalling, light, medium, severe. So we categorize the spalling damage based on this one. Okay, this is oh sorry, this is the crack, not spalling. Okay, so we measure is basically we need to measure the damage to categorize this one. Okay, so my research is to streamline or automate this process by using the new sensor and some kind of the mobile platform, drone or robot, or the computing resources. Okay, so basically I'm tackling the how to streamlining data collection, damage identification, or the once we found the damage, we'll find out the location of the damage. Okay, and also I'm more focused on the how to quantify the damage. Okay, so that's the process. I'm trying to using some kind of computer vision algorithm to address this issue. Then after I joined the Waterloo, I had one phrase at the end, collaborating with a human, which means, although we have a fancy algorithm, fancy hardware, human engineers, at least one human engineers actually go there and then do something. So I'm trying to think of how to leverage their expertise to do the inspection. Yeah, that is the focus of my research. Okay, so I'm going to introducing the 3 projects. Okay, first project is the image scale estimation. To answer this question, can inspector measure the size of the damage from just a regular photo? Okay, no special hardware, just a regular photo. Can you measure the size of the damage on the photo? The second project is the real-time, the quantitative, the visual inspection. So can inspector to measure the size of the damage right away using the new hardware? So I'm using the mixed reality headset. I mean, Microsoft the HoloLens for this project. Then project 3 is how to measure the volume. So the reason I measure the volume is, if you see this guideline, so many people is working on measure the size of the damage, but in the manual, we need to measure the depth, right? It's like a 3D depth for the damage to categorize this damage. So we developed the technique, to measure the volume of the damage. Okay. Okay, I first introduced the first project, the image scale estimation. Okay, a lot of the people in this area is working on developing some kind of the image-based solution. For instance, image classification to see if there's a damage on these images or not, and the object classification, and then we call this the bounding box applications. So where is the damage on the photo? And also people is working on the segmentation. The reason we are doing the segmentation is to measuring the size of maybe the spalling. We need to do the segmentation, right? Okay. But problem of this method, it's not a problem. It's like a issue of this application is all this in the pixel unit, okay? So this size is a pixel unit. We need to convert this pixel unit to the physical unit. For instance, what is the actual size of this spalling area? To get those translations, we need to find out the scale of the images. Okay, one simple way is we can take a photo with a crack gauge or the non-dimensional object so that we can find the scales of those images so that we can make a measurement. Or so we can use some kind of the new hardware, stereo camera or depth sensor. Or recently, the iPad or they're equipped with a LiDAR sensor to make a measurement. Okay, but my question is, I'm just without using any hardware, I just want to make a measurement purely on these images without using any new hardware system. Okay, but the problem of this one is here I can measure the size of the length of the crack or width of the crack in the pixel dimensions. How to convert from the pixel to the real dimension? I'm calling this one is a scale. So if you know that this one is identical scale, we can just multiply this is a scale value and that become a physical value. So the question is how to find the scale of the images, okay? So this is the key ideas. I'm going to give you a quick question. So I take a photo, this two photo in the same location. Can you identify which one is a more capturing the closer distance? We can easily identify that, right? This one. The right images in the is like a capturing the closer distance, okay? We don't have any context, but we can find this depth perspective by comparing these two photos, okay? Which means we can get the depth perspective based on this texture information, okay? If your texture is a large, is a capturing the closer distance, is a texture is a small, and when this so grain is a smaller, we realize that this is a far distance, okay? So my idea of this research is by analyzing this texture and then estimate the scale of the images. So I'm going to use this convolutional neural network to build this prediction model, but I'm not covering what is a convolutional neural network, and I think the previous presenter already explained that. So I'm just training this convolutional neural network model to estimate the scale from the surface texture, okay? Okay. Advantage is I just need just a regular camera and to take a photo, but we need a one-time training process, okay? If we build a model, we can estimate the scale everywhere on your structure, okay? And once you get the scale of the images, we can make a measurement everywhere on these images, okay? And also I didn't mention that this one, we can manually, make a measurement of the crack length, or we're integrate some kind of other automated algorithm to automated quantify the damage, okay? But there's a two requirement. I mentioned that once we train the model, we apply this model to the other area, which means the surface, the texture pattern should be similar. I think that this is a reasonable assumption that, let's say, when we build a bridge, we are using the similar, the mixture of the concrete, right? So the texture pattern is similar to each other. And the other requirement is the image should be taken parallel to the scene, which means if they're parallels, all the scale values are identical, okay? That's why we need this two requirement to use this model, okay? So this is the overview of the proposed system. Take a photo, and then we manually or automatically segment those area. But right now, this one is a pixel unit, okay? Then we extract the patches from the texture in the background outside of the damage. This is ABC. We are putting in to the trainer model, and then this will give you the scale values of the images, okay? And then we multiply this scale value to pixel value, we can get the damage information in the real unit. Okay. But to develop this model, we need a one-time training process. Okay. So how to train the process? We just need only the marker. We put the marker on the structure and then take a photo. We can, the marker detector automatically detect a marker. And then we already know the size of the marker. So, which means we can extract we can get the patches and then corresponding scale automatically. So we build this database, patches, and then those scale value. And then we train this CNN network, VR estimation model, so that and the new texture comes in, we can estimate the corresponding scale. Then we validate this methodology in 3 different cases: pedestrian bridge, building wall, asphalt to pavement. Okay. So if you see this, if you take a photo in the closer distance, if you extract the same size of the patches, you can see that they're obviously different, right? Which means that we are let the prediction model is to find out to do the difference to estimate the right scale value. Okay, that's the underlying process. Okay, to train this model, we used this mean average percentage error loss function. So at the end, we use the mobile net to train this network. So here's the details of the training process. But here, I decide what was the size of the patch they extracted from the background. Okay, so I tested the 3 different patch size. Okay, but obviously, if take a large size of the patches, they include the more texture information. So which means they're producing the higher accuracy, highly accurate, the scale value. So this is a loss curve, see the 850 is the optimum size of the patches. So, and then we validate this one for the 3 different data set. And then, one thing I want to point out is, so let's say the location of the training and then testing locations are different. So that's why in the scene means I put the one marker and then collect the data, and then I move the location and then put the marker and then collect the data. And then I separated training and then testing by scene, not the photo, so that the testing scene is not seen on the training phase. Okay, so here's the result. This is the training and then testing, and then this is our final result. The accuracy is around the less than 50%. Okay, that's not super accurate, but this is reasonably accurate. So which means if with this model, we can take a photo, we can measure the the size of the our damage with this accuracy. Okay. Okay, so I'm going to move the second project. Okay. So the previous one is I need to train, although we are using some kind of regular camera, but we need to have some kind of training process. Okay. But this one is I want to develop some kind of system. I want to measure the size of the damage right away in the field by bringing in the new hardware system. Okay. I'm using this mixed reality headset. Okay, I'm just the difference between extended reality is like an umbrella term that include virtual reality, augmented reality, and mixed reality. Okay, but the difference is virtual reality, all these are virtual. Augmented reality, we just overlay the graphic on the scene, But the mixed reality, we need to understand the scene. So if you here, so basically we're placing the graphic on the scene. So that's why if there's a front object, so this mixed reality has to do not, the visualize this area. Okay, that's the big difference. Okay, basically mixed reality headset construct the 3D scene so that we're placing the graphic with a special awareness. Okay. So Microsoft HoloLens 2 is the state-of-the-art mixed reality glasses that they have such a feature, gesture control, head tracking. Head tracking means we are tracking the poses of our devices. To do so, we need to construct a 3D map so that we find out the poses of our device onto the 3D map. Okay. So the objective is I want to develop the real-time and the interactive visual inspection system using the XR headset. Okay. But the key part here is interactive. Okay. The reason the interactive process is needed is I realized that all this, the current damage detector is not 100% accuracy, right? There is some kind of weird segmenting the damage area. Sometimes it fail, okay? We need to some kind of the modified, improve those, the detection results. So this system is allowed the engineer or the inspection in the field to modify this, this outcome from the algorithm. That's why we are saying the interactive visual inspection system. So this is our interface. So we are using the interactive segmentation algorithm. So that requires the user's input. So we put the seed point inside of the damage and the seed point outside of the damage. And then this algorithm is automatically segment this area. But if you fail, if the outcome is not perfect, we can improve this one interactively. Okay, we can add the more point on the spalling area. We can get the good, almost the perfect shape of this area. And then I mentioned that this one is head tracking and then special mapping, so we can measure the size of the damage as well. Okay, so here's the demonstration of this interactive part. So we pick the seed point inside and outside. And then this area is automatically segmented, okay? And then you can measure the size of the area as well. Okay, here's the process pipeline. But I'm not getting to the detail of this process pipeline. But the point is, in this project, we're going to make some kind of the basic framework. Okay, I realize all this segmentation algorithm, the detection algorithm is computationally expensive. Okay, it's sometimes it is required the GPU or sometimes it's high-end CPU. Okay, so we are setting up the the offline the computational server so that we can just send the data to the server and then process them and then get those only the output, so that the inspector or this HoloLens doesn't carry on the high computational power. So that's this drawing. We are applying this process. Okay, so we used this FBRS algorithm. Okay, but I skipped this part. So this one is that we studied how many seed points is needed to get the perfect boundary of the spalling area. Okay. So here, let's say this segmentation algorithm is get the boundary. So we need to measure the size of the damage. Okay. So what we did is we get the boundary pixel of this damage area, and then we are get the to get the real size of this maybe the spalling in this case, we need to get the 3D points of each pixel location. So we use the raycasting algorithm. So all this photo is tracking the position, which means we know the pose, we know that this P projection matrix. So this raycasting algorithm, we projected this ray to the 3D scene and then point that the cross to the mesh. Mesh is the 3D environment. In this case, this spalling boundary, okay, to get the 3D point. Once we get the 3D point, we find out the surface that placing on this damage boundary, and then project all this 3D point on this images in the plane and get the area. Okay, this is the okay. So this is I want to the test the accuracy of the Hololens, because they're not publishing any of the this accuracy testing, but this one is we set up the 50 centimeters, the 2 marker, and then testing this accuracy of the measurement, but that is less than 2 meters. Okay, so this is the field testing, and then using this marker, so we get the ground truth, the size of the spalling area, and then we use the HoloLens rather than there's no network conditions, so we bring our laptop that is assigned as the computational server, and then this is the accuracy. So this is the ground truth. That this is our measurement. So error is less than 10%. Okay, it's pretty good. Okay, so this is the 1-minute video that summarize all this work. So can I share the sound?
Bridges all over North
Can you hear
America
the
are
sound?
aging
Okay.
very rapidly. Therefore, the cost to maintain these bridges is also skyrocketing and is becoming unsustainable. Right now, bridge inspections are time-consuming, costly, and very inefficient. To solve these issues, we are using the Microsoft HoloLens 2 to allow inspectors to measure the sizes of structural defects as well as collaborate more effectively with each other. The HoloLens 2 is a mixed reality device that lets users see and interact with holograms using hand gestures or speech commands. We use a technique called interactive segmentation. The user first selects a few points inside and outside a region of interest, and then an image processing algorithm analyzes the image to segment the defects more accurately. Inspectors can also add 3D text annotations on objects of interest, which can be viewed by other inspectors wearing a HoloLens. We hope to provide inspectors with a solution that improves inspection outcomes, such as increased accuracy and efficiency, as well as increased collaboration between humans and technology. Thank you for your time.
Okay, so yeah, I'm going to finish my final work within 5 minutes. Okay, so I'm trying to streamline this OC manual process. Okay, but I realize that they ask this depth measurement. Okay, to categorize this degree of the damage. Okay, the problem is the HoloLens is a pretty good accuracy. I don't know the exact accuracy. This one is I found from some kind of a conference paper, but the 0.5% of at the 4 meter, that is around the 2 centimeter, but that's not high accurate, because this one is required the 2.5 millimeter accuracy, right? And also the larger sensor, but that accuracy is a 2 centimeter. So this is not good, right? So both are not feasible for this levels of the accuracy, the depth measurement. So what we're trying to do is we already know the poses of our image from the HoloLens, and then we're using the structure from motion and then reconstruct this damage, only the damaged region, and then evaluate this 3D analysis, making a depth measurement or making a volume measurement. Okay, that's this research, this project. Okay, but the problem of, we are preparing the paper for this one, but we wanted to do the accuracy testing, but we don't have a this the 3D sensor that high accurate. So we first collect the data from the spalling, and then we have a the computer model, and then we are making the 3D, we 3D printing of this spalling area, because we already have a computer model. We know the exact volume and the size, and then we apply the the texture, the concrete texture paint, so they looks like a realistic. So we are testing our system using this specimen. Okay, so here's the step. We collect the multiple images from the different angle, and then run the SFM to get the 3D point cloud from the scene. That scene is included in the spalling area. Okay, and then we do the segmentation. We use the interactive segmentation. We apply some kind of automated segmentation, where we manually segment those areas. Okay, and then we are meshing. We are build the 3D models of only the damaged area. Okay, and then we are to compute the volume. But in this case, we are finding how much material loss in 3D. We just know the hypothetical plane, so that we find out the loss. Okay, and then we compute the volume. Okay, so here's the experiment. So we wear the HoloLens and then take a photo, and then here's the list of the photo, and then we'll run the SFM to build the 3D point cloud model. Okay, and then we do using the interactive segmentation. We are segmenting those areas. Okay, and then we get the point cloud inside of we get the point cloud inside of those damaged area. That is the point cloud that we are using for the the damage modeling. Okay, so with this point cloud, where we are meshing this point cloud, we get this 3D model. Okay, so but this is just a damage model. To compute the volume, we need to know the surface. Where is the surface of this damage is presented? Okay, so to do so, we need to get the 3D point cloud at the boundary, because that there's a spalling here. Boundary is a point cloud in the boundary area is a place on the plane, right? So we fitting this point cloud and get the plane, and this is the plane, and then this is the volume. So once you get this hypothetical plane, the fitted plane, and this ABC is the triangular mesh, one single mesh, and then we compute the volume. Okay, we repeat this every triangular mesh on the damage area. That's the volume of the the damage. Okay, so this is the sample result. Okay, so the error in the volume is around the 10%. This is the plane area. Okay, so and then this is the volume estimation accuracy depending on the distance. Of course, the far distance is lower than this one, but there's a trade-off. The damage is getting bigger and bigger. This accuracy is higher. But there is a longer and longer distance. The accuracy is going up. Okay, so I'm going to present this in upcoming the conference, and I want to finally mention. So this one. So this one is you can see all the script and then data from this GitHub repository. And this one, this paper, we already posted all the script and then data to this repository. Okay. Oh, sorry. Thank you for the listening my presentation. And this is my students. One student graduated. I'm working with the 3 PhD students. My colleague, the Shimon is in move his position to the UCLA. I co-supervise some of the students with him. Okay, here's my funding agency. Okay, thank you for listening my presentation. Okay.
Thank you very much, Chul-min. That was a fantastic presentation. So we have a short couple of minutes to allow for questions. So if anybody has a question, they can either raise their hands or just turn on their microphones and ask whatever you would like. So I'm going to allow for 10 seconds if somebody is going to wants to ask, and then if nobody, I will ask the question myself. Anybody have a question? So I will ask the question that I have. Oh, there's somebody. Okay, go ahead, please. Thank you.
Oh, I'm sorry. I'm sorry for the interruption.
No, go ahead.
Okay, first of all, thank you, Dr. Schott, for the great presentation, actually, and for the great research work. It's really amazing and impressive. And I was thinking that what is the possibility, like since in construction engineering, to extend project number 1 about the size of the crab, to extend it to something like finding quantity takeoff in general, not only for the damage, but for the quantities of the walls, doors, windows, and etc. So what are the possibilities that something like this could be extended?
Yeah, I haven't thought about the construction project because, this one is used for some kind of inspection, because construction project, if the object is too much far away from your location, it's not easy to take a photo in the parallel to the surface.
Yeah.
So
Sure.
I mean that it's not easy to use this one, but the reason I developed is that this one is just use a regular photo. And then I'm trying to expand this research for the zoom camera. Let's say there's a damage on the remote area. I mean, there's no way to measure the size of this damage. So using the zoom camera is zooming out those area. Using the texture, we get the scale and then make a measurement. That is, that is the expansion of this one. But yeah, I haven't thought about the construction, the.
Okay, thank you so much.
Can you hear me?
Yeah.
So perhaps I have another question regarding, let's say, to comparison with the already available long-time tools of non-destructive evaluation. What will be the, let's say, the pros and cons in compared to, let's say, quite established techniques that use, I don't know, wave propagation tools and so on?
Yeah, but the levels of the accuracy is different. So this one is, I mean, some kind of the NDT method is some kind of the inspecting some kind of the damage inside of the concrete, indeed, like a delamination, right? But this one is, I initially mentioned that this one for the visual inspection. Okay, I'm just my initial motivation is how to streamline this process. They're right now they're manually measured all this, the damage on the size. I'm just trying to, to figure out that this one using this new technology. Yeah.
Okay. So you think Chul-min that there is a potential of kind of merging this stuff? So what you have presented stays mainly on the surface, but potentially this could be, as a methodology, something that could be applied, let's say, to wave propagation methods. So if I give you an image of let's say, of what happens in a reflection level inside the material, inside the levels of material, will that, let's say, be something to consider? Let's say, to adapt your methodology to something that gives information from inside the material.
Yeah, so my master's research is like working on the lamp wave to inspect some kind of composite material, but I moved to this research area, as a PhD. So I mean, I saw some kind of research project that analyze, to convert some kind of time signal to the the time frequency domain. There's like a spectrogram. It's like an image, spectrogram images, and then analyzing those images for damage. I saw those work, but I didn't keep track of those research for a while. But that is possible. Yeah.
Okay. Thanks, Chul-min. I guess, Christian, we don't have much time. I think that Wei is already online. Yeah, you are muted.
Yes.
Yes, correct. You are
I
correct.
don't know if we should proceed with Wei. Hi, Wei.
Yes.
Hi.
We should
time
start.
no see.
We should start with Wei's presentation. We
Okay. Thank you
Dr.
for
Yeum
listening to
very
the
much.
presentation. Okay.
Thank you
Yes,
so much.
I'll
thank you
stay
very
here.
much.
Yeah.
Thank you so much. If anybody has any further question for Dr. Yeum, you are certainly welcome to contact him directly by email. He has all his contact information in the website of Waterloo University. So you can just shoot him an email and he will be happy to address your issues. So on the second conference today, we are going to be welcoming Professor Wei Song, who is also, like Chul-min, a personal friend of mine and a colleague from the time where we were PhD students. And he will be discussing a very, very interesting topic. I am just going to do a very short introduction of his bio. Okay, so he's an associate professor in the Department of Civil Construction and Environmental Engineering at the University of Alabama. He holds a Bachelor of Science, a Master of Science, and PhD. The latter of which he obtained from Purdue University, working under Professor Dyke's supervision. And his interest focus in structural dynamics, structural condition assessment, vibration reduction, advanced dynamic testing techniques, and cyber physical testing. So given the short time we have, I'm just going to wrap it up and give the floor to Professor Wei Song for today's presentation. Welcome, Wayne.
Oh, thank you, Christian, for your kind introduction. So, very glad to be here. So, should I just share my screen to get started?
Yes, please.
Okay. So, I assume you can see the screen, okay?
We can, yes.
Great. So today, with this opportunity, I would like to share with you some of the research that we have been doing using deep learning techniques for correct segmentation. But I came in late, but I saw Chul-min's presentation was very interesting, and then also laid some foundation for my discussion here. But our applications mainly use roadway images. Okay. Now, before I get started, I would like to acknowledge that the research effort here is mainly coming from two of my students. First one is Sean Lin. He recently graduated from University of Alabama, and then he's currently working at University of Hawaii as a research associate. And the second one is Carlos, and Carlos joined the department, joined my group about 3 years ago, and then he is also working on deep learning related techniques. Okay. Now, I'm going to break up today's presentation into 4 different chapters, but my focus is towards the last part. Okay, in the first 3 chapters, I will share with you some of the developing process of how we come to realize deep learning, the power of deep learning in trying to do the crack segmentation for roadway cracks. And then in the very recent research development, we were able to do a benchmark study, and I would like to share with you some of the recent results from this study. Okay. Now, I saw Chul-min did a very nice coverage on the terminologies regarding the image-related techniques already. So I'm going to just take you very quick through what we're trying to do here. There are mainly 3 different types of approaches for crack identification or defect identification. The first one is simple classification. By looking at the image, the computer algorithm is going to be able to tell you is it correct or not correct. Basically, is a binary output, 1 or 0. Okay. Now, the second type is a little bit similar to the first one, except it is a slightly bit more advanced by doing, okay, not only I can tell you if the image has a correct or not, but also I can actually box the image and then to tell you where the damage is likely going to be. So this is a object detection problem. And the last one is the crack segmentation. This one is basically evaluate the images based on pixel level precision or resolution. So the crack segmentation carries the most information and is also the most advanced technique that we're trying to work on right now. Okay. So this one, again, provides the highest resolution. Now, a little bit more background on this is the equipment we're using trying to capture the roadway data. We mount a 3D laser camera on top of van. So as the van is driving on the road, we're able to pick up the roadway image. This specs on this is about this one every time is scanning a 4-meter laser line, because 4 meter generally is the coverage of one single lane on the highway. And then in this each line, we can cover 496 data points. Okay. Now, this is the typical data we're able to capture. This camera is capable of obtaining both intensity image and a range image, where people sometimes would call depth or terrain image at the same time. And then we can, for each rung, as you can see at the bottom, we can capture the entire roadway profile with every single piece. You can look at both intensity as well as the range image. Okay. Now, where you see a little bit red color, that means the distance of that surface is a little bit higher or closer to the camera. And then where you see the blue color is where the terrain or the position of that part of the roadway is a little further to the camera. Okay. Now, to proceed with the techniques we have done so far, first we started with simple image processing techniques. Now, in front of you on the bottom left, this is a typical range image that we have obtained through the data acquisition process. Now, in here, you see some of the issues. In order to get the cracks from this range image, well, I think by your eyes, you already can see the cracks. Now, these cracks are usually displayed as a sudden change of the range information or the terrain information. However, there are disturbances existing in these images. For example, as the earlier you observed, the surface is not entirely flat. Sometimes you see the changes to go some surface oscillation or variation. Now, this kind of variation is going to disturb the results if we're trying to just allocate the cracks based on the surface variations, because these variations are not cracks. So how can we get rid of those? Okay. Another part of the problem are some man-made feature. So I would like to get your attention to this square box over here, which is bowled up, and you can clearly see the crack in there. But with the crack, you also can see some textures. Now, these textures are, if you're familiar with the roadway, then that's sometimes the Department of Transportation, they would create some kind of grooves. They create a grooves on the roadway so that they can increase the traction between the tire and the structure. Okay. Now, this kind of grooves, again, indicates a change of the terrain information, and it might also affect your identification on the cracks. Okay. Now, therefore, what we're doing is at the beginning, we did the frequency domain filtering. We're trying to get rid of these features. Once we go through the frequency filtering, you see the entire image looks like as a uniform color, relatively uniform. Okay, so we remove the oscillation of the surface, and then secondly, the grooves are no longer, it's very difficult to tell. Now, what we did is we basically used high frequency filtering and frequency harmonics. We removed those information. Okay, remove those information. And then with these images, what we're able to do, we're using a contour-based correct identification. Once you got a contour map, then once we do a frequency cleanup, you can clearly see the cracks are nothing but contour plots, just like how one would highlight in a map. Okay. Now, so the advantage of doing some stuff like this over the traditional methods is this is relatively insensitive to varying lighting conditions, because most of the research they've been doing a few years ago, that is, they are mainly using the photos, which are intensity based. But this time, the research we're doing is using the terrain information or the 3D information of the image. Okay, so it's relatively robust. Now, this result is already documented or published in a paper in 2020. However, these method has some issues. So I already said there are two advantages that the traditional method doesn't have, but they also have some issues. The first issue is it does require a pre-processing process. Okay, so that sometimes is trouble, additional work. Besides, in order to do the pre-processing, you have to change or select certain parameters. For example, what kind of frequency you need to get rid of. Okay, and when you create a contour, how deep is the contour cutoff? Now, these kind of parameters, the user has to make a subjective choice, and again, will bring in further uncertainties. Okay, now in order to solve that issue, let me bring you to chapter 2. That is, we start to moving away from common image processing technique to deep learning based correct segmentation. Again, still using range images. Now, the way it works, which I think is relatively similar to almost all the image-based deep learning processes, we break things up into two phases. First one is training phase. Second is prediction phase using trained network. So in the training phase, we are going to have our acquired image, and then we develop a labeling, okay, come up with the ground truth label. And then using the labeled data with the collected data together to do the deep neural network design and the training. Once you have the trained network, we're going to do the testing, okay? And for prediction purpose, okay? Now, some of the results to share with you real quick. Now, once you obtain the image data, again, this is the range image, you don't need to do any processing, just the raw range image. We can get a very clean crack map, very clean crack map. Obviously, what's the advantage is comparing to the frequency-based method, we no longer need any pre-processing. And because of that, we reduce the subjectivity, okay? You no longer need to pick all these filter parameters, okay? Now, results, again, is documented in a paper in 2020, okay? But this technique comes with limitations as well. Now, in front of you, what I'm showing is there are 10 image patches, okay? On the very top row, that's the image patch, meaning the data we work with. Second row is the ground truth. So if you really look closely, right now, they look very small, but actually they're really high resolution. So if I display that picture in front of you using just one computer screen, you can see these cracks. So that's how we're able to do the ground truth. And then the last row is what our neural network can do. Now, you can immediately see the problem. You see, we're missing several cracks here. And then, why is that? by taking a look at the raw data, you probably can guess what happened. For example, in this one, right? This one I'm pointing at right now is actually very hard for you as a human being even to see that crack with a very rough look. Okay, that's why it's missing some of the details here. Same here. Okay, therefore, with these kind of cracks, which they have a very relatively shallow profile, it's difficult for you or for the algorithm to capture the crack features. So that's the challenge. That's the challenge. Then we were thinking, so what can we do to address this problem? So our solution is we're trying to use a cross-domain data fusion because, as you can see here, earlier I mentioned when we collect the data, we actually collect both intensity image as well as the range image. If something cannot be seen clearly from the range image, maybe I can see that from the intensity image and vice versa. So is there any way that we can leverage the both data set to do the same job? Okay, so that would lead you to our our next topic. Now, before then, let me give you a brief summary. So far, by using DCAN, we can get rid of the dependence on subjective parameter selection. However, it does bring in more problem that is hard for us to address the feature when you have shallow cracks. Okay, so in order to solve that problem, we developed the data fusion technique. Now, this data fusion technique basically is the leveraging both the range image as well as the intensity image, and then leveraging their property that is spatially they co-locate at the same spatial location. And then we fuse the image into a new data format. Now, this kind of data format contains the information from both the 3D terrain as well as the 2D intensity. And then with that, here is our result. So this is just one result, okay? So the first picture from the left, the first picture is the data. And then the second picture is the result by using the range image alone. The third is using the intensity image alone. The last one is use the fused data set. So what I want to bring your attention to is you see these metrics, F1, IOU, BF, which I will be introducing them shortly. These numbers, the higher the better. 100% will indicate perfect performance. So as you can see, range image generally get better performance than using the intensity image, but the fused image get the highest accuracy, okay? BF value beyond 90%. So with this, what we have discovered is by fusing two different data sets together, we're able to achieve the highest segmentation performance. Now we leverage the cross-domain features or correlations, trying to reduce the possible disturbances. Now the results has been documented in these two papers from 2020 and 2021, okay? Now here is basically, this is where we're at. So we're able to develop a DCAN using fused data images. Now this is where we can address most of the challenges that we have seen so far and got good results. Now using this, actually, I'm going to bring you to the last part that I would like to spend a little bit more time with you today. Now, based on what we have learned so far, we did some review study. So what we have found out is, first of all, there are not many publicly available data set that has both intensity and range images. And to be honest, there is just not many data sets for range images, period. Okay, most of the publicly available data sets are captured using camera with intensity images. Okay, so not many even have the range information, meaning the 3D information. So that's what we have found out. And then that lead to the second point. That is, most of the current development on DCAN-based crack segmentation, most of the studies so far, they have never do a benchmark study to use one benchmark data set to compare all the existing dominating networks. Now, part of the reason is because there are not many range data set available, okay? So therefore, that motivates our study. So we're looking for a thorough investigation on the proper choice of image data types, because now we start to see the advantage of using range image, meaning 3D versus 2D. But there are just not many comparison has been done on which data set actually is more useful or valuable, okay? And then earlier you saw when we fuse the intensity and range image data together, we're able to get better performance. But that's just for our network, the network we designed. Is that the power from the network we designed, or that's really the power of the data set? We don't know that. If it's the powerful data set, then this idea may be applicable to other network as well. So that's something we would like to find out as well. So this motivates our chapter 4 study here. We're trying to do benchmark performance comparisons. So with that, I would like to first to tell you there is a data set we have already released to the public. And then here is the DOI. This data set is, we dubbed this data set as FIND, find, okay? This data set contains 4 different data types. One is a raw intensity, second is raw range, third is the filtered range, okay, filtered data, okay? And then the last one is the fused image by fusing the raw intensity and the raw range together, okay? Here are some properties, and this is the DOI link, okay? Now, we also pursued 9 prevalent popular networks. Okay, these are the 9 networks we have compared in this study. And then the last column indicates how many parameters in describing each network, okay? So as you see, the number 6 is really has a really much more parameters than others. And then number 3 has the least number of parameters. Okay. Now, what we are doing with this study is we got our data. And with our data, we have done 4 different preparations. The first one is we provide a filtered range. Second is just a raw range. Third one, the fourth one is just the raw intensity. And then the third one is fuse the 2 data set together using the spatial co-registration that we demonstrate in the publication. Okay, so we have 4 data sets. Okay, we have 4 data types. 4 different data types, okay? Again, these 4 data type is already released in the find data set, okay? And then what we're doing is we're gonna inject this data, okay? Prepare them with ground truths and then do all the necessary training process with 9 networks. And then we're going to evaluate their performance, okay? Basically, the performance of 9 networks with 4 different data types. Now, here is how we're going to do the performance evaluation. I apologize, I put this slide a little bit later. I want to just get your attention right now. But we already used some of these earlier when we were trying to demonstrate how good the performance is. The first is the precision recall analysis. Here, most importantly, is the F1 score. And then the second is intersection over union, okay, IOU score. And then the third one is the boundary F1 score, BF score in short. Now, all these are mainly be defined based on the results in terms of true positive, false negative, false positive, and true negative, okay? So these matrix has been commonly used in many of the DCNN studies, so I'm not going to explain the details here. However, there's one we specifically done in this study is to use the performance precision recall curve, or in short as a PRC, and then the area under the curve to evaluate the performance. So what it really means is we're changing the threshold setting in the network, and then we're trying to use that to see how robust our network is. Now, just so you know, the higher the value on the F1 IOU or BF value, the better. Now, regarding the area under the curve, the larger the area, the better, because a perfect classifier, as you see here, is indicated as the green color classifier, would occupy an area equal to 1. Okay, so that is the highest performance you can ever achieve with the AUC. So these are the performance metrics we are using in this study. Now, here are some of the results. The results on the accuracy. So let me try to help you to navigate the graph a little bit better. So in here, 3 charts. The 3 charts we display the F1, IOU, and the BF scores. Okay, and then in the horizontal axis indicated the 9 networks we have. And then each bar indicates one of the data type we used. So what we can learn here is consistently, we can see fuse the data set, which is the purple column here, or purple bar, is the highest, okay, for each of the network, and does not matter what kind of performance matrix you are looking at, okay? So within each little group, the purple bar is the tallest, okay? So fused image really leads to the best performance. So this is a very strong proof. The second is the impact from pre-processing, meaning filter the data, really does not show very obvious impact, because the orange bar, which is from the raw data, versus the yellow bar, which is from the filtered data, they are almost the same height most of the time, okay? So that means if you use DCNN technique, perhaps you are not going to need any filtering, okay? Now, out of these, there's another important information that's, we can see possibly these 3 networks, that's the crack fusion net, UNet, FCN, and the deep crack are the winners, Here, the crack fusion net is the one that we developed, okay? This is the one we developed. Now, to reinforce the results, I'm taking you to see the histogram. Earlier, what you saw is the average. Now you see the whole results in front of you as a histogram. Again, what you can see is by comparing to, so each row corresponding to the network, each column corresponding to the comparison. So the fused data really get better performance. However, filtered data versus the raw data does not show big difference for most of the networks, okay? Now, we zoom in a little bit. We're trying to find the winners. So we already identified using fused data can give us the highest accuracy. So let's just look at the fused data. Now, in front of you, these are the 3 performance matrix with 9 networks when they applied to the fused image. And then you can see there are 3 winners consistently showed up. They are the UNet as the number 1, the tallest bar over there. Crack fusion net is the blue color bar, usually, is consistently shown as the second best in terms of almost all the 3 performance metrics. And the third one is deep crack. Now, by looking at accuracy is not enough. Let's look at how efficient they are. So the top 3 networks, well, all the results are shown here regarding their training time, but we summarize the top 3 winners here. The top 3 winners are Crack Fusion Net, VGG19, and UNet, okay, in terms of the training time as well as the testing time per image. So it's very, very impressive for you only take 15 milliseconds for you to go through one patch. So you can mark the cracks with that kind of speed, okay? Now, this is a precision recall curve. And then again, the AUC is the one to give the evaluation on the performance, but this is a very similar to the earlier graph. So I'm not gonna spend too much time on this. Again, it consistently shows the 3 winners here. Okay, 3 winners, okay. Now, here are some of the detailed comparison. I'm gonna just point out some discrete examples here. The first one is when you look at each row represent each data set, and each column here represent different networks. So what you can see is if you're using the raw range data only or the filtered range data, you do get some false negatives, okay? Meaning you're missing some of the cracks. You're missing some of the cracks. Oh, by the way, the ground truth on the bottom, on the top left, okay? So, but once you start using the fused raw range data, you got consistently much better results, much better results. Again, this is an example to demonstrate the power of using fused data set. The next one is previously, all these little examples are using one image patch. Here in front of you, this picture is basically one chunk of road. So this would contain hundreds of patches in here, okay? So what we see here again is if you're using just the raw range or raw intensity, you're facing sometimes missing cracks. That's a false negative here. And sometimes you would have a false positive. So where does the false positive come from? Take a look at the image. They come from the grooves, okay? So sometimes if you just use a raw range, you are having this trouble, okay? Now, once you use the combined fused raw image, that's the first row here, that problem get much, much, smaller here, okay? Now, towards the end, I would like to briefly summarize what our findings are. So the first is we are able to develop and release a large-scale fused image data set, okay? And the second is we conducted a benchmark study using this data set. We're using one data set to evaluate all the popular networks to give a fair comparison. The third is the top two candidates in terms of accuracy and efficiency are, in terms of accuracy, they're fairly close, really, okay? Just missing by 1% about. Efficiency-wise, Crack Fusion Net is 15 milliseconds, UNet is 23 milliseconds. And the impact from image data type, we identified that using the fused data set is much, much better than use the raw range or the raw intensity data alone. And then we also find out if you use DCNN, you really do not need to do any filtering or pre-processing, okay? So all the results we have discussed today have been documented in these publications. And then the chapter 4 is actually one that is currently under review, okay? Currently under review. And in the end, so allow me to share with you the data sets that we have developed and shared with the public. The second one is a public data set with the range image, okay? It was released on DesignSafe. The first one is the find data set. Again, it contains all 4 data types, and then it's released on Zenodo, okay? Now with that, I really appreciate your attention and time. I think I'm ready for any possible questions you have. Thank you.
Wei, thank you very much for the very nice presentation.
Oh,
I mean,
thank
it
you.
was, yeah, really cool. I will open the floor for questions. But perhaps I can start by just I have a rather engineering question regarding why roadway? Why road surface roughness?
Oh, okay. So, okay. Now, the Department of Transportation has one of the performance criteria on both the roadway and bridge deck, that is the correct size and the density. So very often, in order to rate the bridge or rate the road, part of the information really comes from the cracking. And obviously the cracking can lead to many potential issues. That's why DOT is very focused on these defects particularly. Now, for example, if this crack happened on bridges, then these cracks can trap water And then in many of the northern states in the United States, they actually using salt in order to increase the traction on the road and the bridges. And then these salt combined with water would get trapped into this crack and then will slowly to corrode what's inside of the deck or underneath the roadway. Now that's why DOT has published a menu from the ESPOL code, a menu trying to capture the rating on crack size, meaning length, width, and density, meaning what's the roughly spacing of your cracks. So these are the reasons that we are working on trying to capture this information efficiently just from the images. Yeah.
Okay, I see. Since, I mean, one, let's say, side project of our research corresponds to kind of the measurement of the road surface roughness. So let's say the profile, vehicles are more like buildings with earthquakes, right? So you need, let's say, to estimate the road roughness, the road profile that actually excites the whole dynamics of the structure. Would that be indirectly useful for such a measurement, taking into account, okay, that we have the suspension system and the vehicle own dynamics? But will that be, let's say, something as a side measurement?
Yeah. Actually, that's a very good comment, right? So to be honest, if you look at the data, not only we are able to capture the crack, we are really capturing the entire profile of the road. So the question on the roughness is more about profiling of the road. So yeah, the roughness really comes with the driver's comfortness, or, sometimes the roughness is also an important criteria for roadway construction as well, meaning, what's your experience with your driving? Yeah.
Yes.
So, and then you can see many of the problems with roadway is, I did not include that here, but for roadway engineers or pavement engineers, they would have a common issue called rotting. That's what the tire has been used mainly on the certain spacing. And then after a while, you will find a certain part of the road just going down and then come up again. These parts of the road will capture a lot of water, and then it will have a skidding problem. So yeah, all these are related with the profiling issues. And nice. These data sets is able to capture those. You are absolutely right. However, I just want to point it out, the information related to those would be something in the surface variation we're trying to capture rather than to get removed if our focus is the correct.
No.
So,
on my side, just a suggestion, if you already don't know about that, there is an excellent book that is, let's say, early to middle 90s by David Sebon. He is a professor in Cambridge. That it's called the Vehicle Road Interaction Handbook. And it is an excellent analysis, both, let's say, in the dynamics, but also from the pavement side of view. It is very detailed also on the measurement side. I think that if you continue research on that, it will be great. Maybe I can email it to you.
That'd be great.
I cannot find it as a PDF. I have it only on hard copy, but it's an excellent book, an excellent one.
That'd be great. Thank you so much. Yeah, okay. I was not aware of such work has been done at Cambridge before. No.
Yeah. So I don't know if we have any other questions. Maybe Camila raised her hands.
Yes, good morning, Dr. Song.
Good morning.
Everybody here present. Thank you for your presentation. It was very impressive. I would like to ask why use the raw range image with the raw intensity to fuse them and not the filtered range with the raw intensity?
So let me try to understand the question. So let me try to get to the data here. So is your question being why we fuse the raw range and raw intensity? Why not for us to fuse the filtered range with the intensity image? Is that correct?
Yes, exactly.
Okay, so our intention was we're trying to move away from any filtering work, because in order to do the filtering, you have to make decisions on, if you are a certain high pass or low pass, you need to decide what is your cutoff frequency. Now, these decisions require you as the user to make the decision. And that decision will impact your performance as well. So sometimes only experienced engineer, they probably can call, a good threshold for you to cut this off. But in our case, we try to move away from there. We try to say, okay, you don't need to do anything. Just get the data raw without any processing. Just get the data and see what can we do with it. And then since we're trying to do the fusion, so why don't we just use the raw data? So so something directly comes out of the data acquisition system. That's the idea, okay? I mean, also later on, as you saw based on our finding, the raw range, okay? So let me try to just go for that real quick. So the filtered range data in the last column right there. So the filtered range and the raw range data, when they applied through DCN, really generated very similar results. That means the information content in both images has been captured in terms of the crack detection. Okay, so that's actually an advantage for us to use DCN rather than any filtered techniques.
Okay, great, thank you.
Thank you.
Any other question?
I do have a small question, actually.
Sure,
Ray, that was a fantastic presentation.
Thank you.
Can you elaborate a little bit further about the filtering techniques that you use to use the filtered images?
Oh, okay. So let me try to go forward there. Now, so the image we're having here basically is the coordinates are two-dimensional, but the information is on the third dimension. So comparing to, when people study signal processing, most of the data are based on time history. Our data is really based on spatial. And then comparing to most of the people study the filtering using signal channels, which are usually 1D, we're looking at a 2D space because the roadway is really on a 2D space. So in other words, the filter we're doing is a two-dimensional filter, okay? And then the type of the filter is similar, that is, for the surface variation. So what we need to understand, which is also helpful when you design the cutoff frequency, meaning user choices on these parameters, again, we need to recognize the information contained by the cracks usually represent a sharp change in the data. A sharp change in the data usually would represent a combination of low and high frequencies. But the roadway oscillation comparing to such a sharp change usually corresponding to rather low frequencies. Now, because of that, we can set up a high pass filter to get rid of some of the surface variation information and just to preserve the information on the crack. Okay, so that's how we change the colorful picture from the left to something with just a unicolor. That's the blue color, which is relatively around zero. Okay, zero oscillation. Now, regarding the groove pattern, here what we can observe is the groove pattern using filter language is nothing but a repeated harmonics or repeated pattern. Now, in that 2D space domain, that will be represented at a particular harmonic frequencies. Therefore, all we need to do is to design the proper notches to get rid of these harmonics. Now, that's how we removed all these grooves. So once you see on the picture on the right, you no longer see these clear periodic pattern in there. But to be honest, you cannot do that perfectly. That's the problem with doing filtering. Lots of the assumptions are pretty mathematical and ideal. Even if you come up with a good assessment, to notch out a range of the frequency, you still cannot do things perfectly. So.
Thank you very much.
Sure.
For the response. So I believe we have achieved our goal of finishing both sessions by 12:30. It has been a fantastic session today. Thank you all for your patience and for your staying until the end of the presentation. I'm gonna reiterate briefly about the availability of information that we have in our website. These 2 lectures are going to be uploaded there as a recording, so you can actually download it and enjoy them privately and afterwards. And we will have a final presentation in a month from now. So make sure you log into MARS-SHM/workshops to check it out. We are going to have the visit of Professor Yang Wan from Georgia Tech and Professor Nikolaos Dervilis from the University of Sheffield. So, and they are going to be talking about the vibration testing and some machine learning techniques as well. So you are welcome to attend and to check this out. So maybe I can leave Vasilis to say goodbye to everyone. And once again, I thank you Wei very much for accepting this invitation and for sharing your fantastic research with us today. Thank you so much.
Yeah, sure. Thank you.
Very close from our side. Let's hope that we can collaborate in the near future. Do another, let's say, special issue or something else. I would like to also thank the attendees for their participation. As you all know, we can always contact in person by emails and so on. So this is just the starting points of these seminars. We can let's say build on that. Have a good morning. Have a nice afternoon, everybody, and see you next time.
Take care, everyone. Bye bye.
See you.
Bye.
Thank you.